constraints. So a design problem consists of these things. The constraints of a design is equally important. While you think about constraints of design, manufacturing constraint was one major limitation when you think about a design. So suppose if you are planning to design something, then this manufacturing constraint was there. You can design many things, but how you will manufacture that? This issue was there few years back. But now this issue, the manufacturing constraint, is not there in engineering design, because nowadays we can say if you can design, you can manufacture it. So that is the major attractiveness of additive manufacturing. The design, the manufacturing constraints of design vanishes because of additive manufacturing. Nowadays, even tabletop, low-cost 3D printers are available. So it is really popular. These images shows two major areas of additive manufacturing, that is rapid prototyping and customized product. Whatever may be the design, you can make a 3D model of that design using 3D printing. That is a well-known thing. Nowadays, even majority of BTech projects also utilizing, undergraduate students, they are also utilizing these rapid prototyping techniques for creating for realizing their designs. The second thing is customized products, customization of products. Dental implants, example, dental implants. Here, there is no bulk production. Each product will be different. That is customized product. These are the two areas where we are getting major advantage from additive manufacturing. See, these are the different products normally manufactured using additive manufacturing. Domestic ornamental items are there. Then, as we explained earlier, these rapid prototyping items are there. Then medical customized product. And in coming to industry, even structural, nowadays, we know the structural components also we are manufacturing using additive manufacturing. See, the metal additive manufacturing components are increasing. The use of metal additive manufacturing components are increasing day by day. This figure shows the increase in number of components, metal additive components, additive manufactured components. Actually, already I presented customization and rapid prototyping are two major advantages. But one more thing is there. That is the reason behind the exponential increased use of additive manufactured components. These are the limitations of additive manufacturing. This is also AI generated. High initial cost is there. Limited build size. We can produce only limited build size. Manufactured components, surface finish issues are there. Additive manufacturing cannot be used for mass production as it is a slow process. So these issues are there, a number of issues are there. Even in spite of these issues with additive manufactured components, the metal additive manufactured components, number of metal additive manufacturing components are increasing day by day. Can you think why this is happening? It is not because of customized product. Another important advantage of additive manufacturing is, I'm coming to it, that the limited build size. Nowadays, additive manufacturing printers, that is 3D printers, are available. The build size of printers are increasing day by day. So the second limitation, we can say we are just overcoming that build size. And the most interesting thing about additive manufacturing is this part consolidation. Part consolidation is the most interesting thing. That's why the number of additive manufactured components are increasing day by day. See, we can consolidate different components into a single component using additive manufacturing. This is the most interesting advantage of additive manufacturing, where suppose if you have 10 or 20 components in a product, using additive manufacturing, you can combine all these components together. And this is the most interesting advantage, that is why the number of metal additive manufacturing components are increasing day by day, the part consolidation. See the interesting thing. This is the three versions of same rocket engine, and the Raptor 3 machine is completely 3D printed. See, the Raptor 1 machine, n number of tubes and components were there, but in Raptor 3, which is completely 3D printed, only limited components are there. So this is the advantage of additive manufacturing. This is due to parts consolidation only. And nowadays, even huge build size machines are also available. I already explained with a slide. Huge build size machines are also available. This is a rocket engine, completely 3D printed in a machine for NASA. So current scenario, this is about additive manufacturing. Then we can think about the current scenario in the total manufacturing sector. See, nowadays, every systems are connected in digital twins. The world is shifting like that. As you know, digital, all the manufacturing process will be normally modeled before we are going for real manufacturing process. The digital tin, a machine, while a real machine is running, parallelly a simulation will be running. Data will be shared between the real system and simulation. Every time, based on the simulation, the real system will be also, the parameters or key process parameters of real system will be modified. Similarly, the feedback from real system will be fed back to the digital system or simulation system. So nowadays, this is the manufacturing trend. Everything is connected to every manufacturing system is converting to digital chip. This modeling of manufacturing system and processes, it can be a manufacturing system, just like a factory that I am showing here. A factory system can be modeled using maybe a MATLAB Simlink, or if it is a chemical system, chemical factory, we can use software Aspen for modeling the process. Similarly, manufacturing processes like casting, welding, everything can be modeled using some particular softwares. This shows some example of some. The first one is showing some casting software, then machining software is there. Q-form, it is a forging software. The bottom one is MATLAB Simulink model, Aspen. So every manufacturing system can be model. The modeling of systems is a vital part of manufacturing system in nowadays. Actually, my basic area of research was modeling of TIC welding only. Actually, in my research area or during my PhD research, what I did is myself developed a mathematical simulation tool using ANSYS for this TIC welding torch, the TIC welding heat source. Um, that was my modeling was my research area. Now, as you know, the whole world is shifting to additive manufacturing. So myself also decided to shift my research area to the additive manufacturing side. Now, about the additive manufacturing, this is the fundamental additive manufacturing thing. There are different techniques in this additive manufacturing area. Selective laser melting or direct metal laser sintering, fused deposition modeling. All these techniques, these things are textbooks items. You know, different techniques used for additive manufacturing. And this diagram shows different techniques in a better manner. Here, my research area was where our research area was welding heat transfer. And in additive manufacturing, there is a promising area called wire arc additive manufacturing, WAM. As my research area was welding, I am simply shifting to wire arc additive manufacturing. So in today's section, what I am planning is to present in detail about wire arc additive manufacturing. As the diagram shows, it is comes under direct energy deposition method. The parallel methods which are considered as direct energy deposition are wire laser additive manufacturing and electron beam fabrication. So these three things are normally considered as direct energy deposition methods. So while comparing performance, normally we will compare these three things. And other additive manufacturing methods like laser sintering, fusion bed, electron beam melting, etc. are different. So we will be in remaining presentation, we will be concentrating on wire arc additive manufacturing. It is a promising additive manufacturing methods, particularly for metals, used for metals. And this is a schematic representation of different techniques. The A, B, C, D, four things are there. C represent wire arc additive manufacturing. First one is laser metal deposition. And for the time, I am not concentrating on the other things. Anyway, this is the schematic representation of basic additive manufacturing techniques. This shows the actual systems and products created using different additive manufacturing methods. So coming into detail, wire arc additive manufacturing. This is direct, as explained earlier, it is a direct energy deposition method. And an arc, an electric arc, or laser beam or electron beam can be used for this method. Both are almost same. Normally, in this method, an electric arc, it can be a welding torch also, is used for melting a material, and that metal drops will be collected on a substrate, and drop by drop by drop by drop building this uh, particular product will be, or particular object will be created. This diagram shows the comparison of wire arc additive manufacturing with its uh, compatible other techniques like laser powder bed fusion, laser direct energy deposition, and electron beam melting. The one major disadvantage of additive manufacturing, the whole processes or the set of processes, is the build up rate. That is the speed in which we can create an object. You think while looking into the third portion, build rate, it's something 100 centimeter cube per hour for wire arc additive manufacturing. While comparing the other things, it is for laser power bed fusion, it is only 50 centimeter cube per hour. For laser direct energy deposition, it is 450, around half only. And for electron beam, it is 1 ton only. And for electron beam, vacuum is another requirement. So from this particular image, we can conclude that depending upon, even if you consider the only one factor, the build rate, this additive manufacturing, wire arc additive manufacturing is having something more potential compared to the other techniques. That is one major advantages additive manufacturing, high build-up rate. How this process works. Here, there will be an electric arc, normally a welding torch arc. To that arc, using a wire feeder, a material will be fed to that particular arc using a wire feeder mechanism. That metal will melt because of the high temperature of that arc, and the molten metal will be accumulated layer by layer. So by layer printing, we can create objects. So this is the simple method of creating a particular object using wire arc additive manufacture. See, this is one experimental object created using wire arc additive manufacturing. Normally, nowadays, this wire arc additive manufacturing will be carried out only using a robot or a particular dedicated machine for doing this process. Normally, we can use a welding robot or a dedicated CNC machine for doing this operation. A welding machine and a controller must be there. Then a robot must be there. The robot and the welding controller must be connected through a computer managed system. Only then we can complete this process. Manually, it will be very difficult for generating a substrate manually using by manual methods. The wire arc additive manufacturing is possible. Theoretically, we can do the welding process and we can do the metal deposition, but practically it may not be possible. Only using a robotic system or a dedicated CNC system, we can do this process. And the welding machine and the robot must be connected through a compatible controlling system. As I already explained, 3 to 10 kilogram per hour metal deposition rate, that is the major advantage of WAM process, that is wire arc additive manufacturing process. The deposition rate or melting rate is very high compared to other processes. And these are examples of some products, some real products made out of WAM process. And this is the bottom one is turbine blade, hollow turbine blade fabricated using WAM process. And as you know, this hollow turbine blade can be fabricated only by additive manufacturing or only by VAM process. Because of its shapes and its hollow character, it can be manufactured only by VAM process. And this schematic diagram shows shows the remaining portion of my presentation. VAM hardware normally includes we'll be discussing about briefly discussing about the VAM hardware system, then different process parameters that controls the VAM process, then VAM's applications and advanced VAM processes in coming sessions. When you think about the VAM system, an arc welding machine will be normally there. Depending upon the welding machine used, we can classify VAM hardware to GTA based, that is gas tungsten arc welding based systems, or gas metal arc welding based systems, or cold metal transfer based systems. So depending upon the fundamental uh, heat source or fundamental welding arc welding machine which is utilized for VAM, we can classify VAM into different categories as this. Actually, the history of VAM begins in 1926. There is a patent in 1926. In 1971 and 83, some initiatives were reported. But this, from this image, you can see there is an exponential growth in number of papers published in this additive manufacturing area from 2010. And this I got from a journal publication, this particular image. The interesting thing is maximum number of papers are published in direct energy deposition methods. In additive manufacturing, maximum number of papers are published in direct energy deposition only. VAM is one of the major direct energy deposition method. So we can say out of additive manufacturing method, VAM have a better future. So this figure shows the current developments in VAM. I will explain it one by one. See this one. This is the, as we started from this particular diagram, VAM hardware can be classified based on the heat source, and this shows different type of welding torches used for VAM process. I am not going to the fundamental welding. I hope majority of the participants know the difference between GMAW and GTAW and plasma welding arc. I hope so. So I am not going into the details of this particular slide. As you know, if it is metal arc welding, the electrode itself will be consumable. If it is gas tungsten arc welding, the electrode will not be, the system will not consume electrode. Electrode will be retained. It will not be melted. Additional filler wire will be melted. And in plasma arc welding, the entire system is different. There, the electric arc is used for creating plasma gas, and that heat of that plasma gas is used for melting that filler wire. So any of this particular arrangement can be used for creating VAM setup. Each one have its own speciality. See, if it is a tick-based system, the temperature range will be around 4,000 to 10,000 Kelvin. If it is a plasma-based system, the temperature will go up to 24,000. So each source have its own advantage and disadvantage. So now coming to the major process parameters related to VAM process. The we know the heart of the system, the heart of the VAM is a welding torch in which an electric current will be converted into an electric arc. The power supplied to the machine will be converted into an electric arc. So the voltage and current and the speed of that particular movement, these three things together, we can say the power input or power density to a particular system. It have three components: voltage, current, and speed of travel of that particular torch. These are the core parameters that design the VAM process. The arc gap, the distance between the substrate and the torch, is the next parameter. And normally in all these processes, there will be a inert gas. In this schematic diagram, you can see nozzles. Through that nozzles, an inert gas will be supplied, and the use of this inert gas for keeping an inert environment during melting. So the fourth parameter is the inert gas flow rate. So we were discussing about VAM process parameters. The most important process parameters, voltage, current, and speed, together it represent the density, the power density, then arc gap is there, and gas flow rate, inert gas flow rate. Similarly, wire feed rather, we have to feed a wire for melting. And that is the another important parameter. So many research publications are there regarding the process parameter optimization. It is an area where research is still going on. I referred some papers published in 2020, after 2020. Still, the parameter optimization is not complete. Still, there is research on this area, finding out the optimum feed rate, optimum current voltage required for additive manufacturing process. This wire arc additive manufacturing VAM process. And this diagram shows the effect of these process parameters on bead width, the metal deposition width, bead width. It is normally known as bead width, metal deposit, width of metal deposited. So this type of n number of these type of studies are available in literature, where these process parameters are optimized depending upon using different techniques and different methods. So parameter optimization is one major area where research is going on in VAM. Another limitation of VAM is the variation of microstructure. This shows, I got from a journal paper, this image. This shows there is a variation in the microstructure of that particular product linearly, because it is created layer by layer. Each layer have a different microstructure. The major reason of this issue is the variation in heat transfer. You know, microstructure is highly dependent on the heat transfer. If the rate of heat transfer changes, definitely microstructure of the final product will be different. Here, metal will be deposited layer by layer. In each layer, the top layer heat transfer will be more. In bottom layers, heat transfer will be less. Likewise, there is a variation in heat transfer. This causes a variation in microstructure. So that is one major limitation of this particular VAM process, variation in microstructure. Even with the limitation, I already explained there are process parameter limitations, optimizations are not complete, microstructural studies are not complete, still going on because there are variation in WAM builded products. Still, this shows interesting products that can be manufactured only by WAM process. It is a hollow pipe. First one is a hollow pipe with multiple branches. Can be manufactured only by WAM process. And this one is a propeller, micro propeller manufactured. And the bottom one is a hollow turbine. It's already explained the hollow turbine blade manufactured. They say these things, this whatever it may be, a hollow pipe, propeller, or turbine blade can be manufactured using other additive manufacturing techniques like laser sintering or power bed fusion. Some metal additive manufacturing techniques are there. It can be manufacturing using that technique also. But compared to that technique, this FAM process is having high deposition rate. So the easiness of fabrication will be more in the case of WAM process. So these are the, even in spite of these advantages or this, um, the major advantage is this complex geometry can be manufactured using this method. In addition, there are these defects are there, still there associated with WAM products. That is inhomogeneous structure. We need post heat treatment, then we need surface treatments for finalization. Residual stresses will be formed normally during this WAM process. Residual stresses will be formed. Then solidification, cracking normally happens. Then porosity is a common issue with WAM process. So these defects are there, still reporting in products manufactured using WAM. So then comes importance of CFD modeling of this WAM process. So even though nowadays we are utilizing WAM process for creating rocket engines. In the beginning, I already explained with a slide. NASA is building rocket engine using WAM process easily. Or the total engine they will be printing in a printer. But still, the research is not complete. All these defects are reporting. So that is importance of CFD modeling or further research on wire arc additive manufacturing. So basically, I am concentrating on CFD modeling and modeling of these manufacturing processes. That's why rather than the experimental studies on WAM process, I am concentrating on modeling side of WAM process. What I am explaining further is purely based on my research. I'm normally working on this CFD, and this is the three levels of modeling that can be applied to WAM process. The first thing is a macro scale. Macro scale means here the welding source, the heat source is simulated, where the heat power input to the welding system will be given, and the heat distribution and all related things, the melting process, etc., will be calculated in macro level of modeling. Second thing is mesoscopic scale. It is an intermediate one. It is what we are doing is we are more concentrating on the melting process. There is a intermediate level. And a third level is there. It is on molecular dynamic simulation. So anyway, during my welding research also, we modeled this particular welding heat source using some um, heat source models, which is available on literature, and it is most widely acceptable. Some methods are there. Utilizing that methods, we can model the heat source, or uh, we can easily represent welding source using some equations. This Goldach heat source model, its schematic representation is here. There is an equation also. Utilizing that equation, we can create the mathematical model of this welding torch. Sorry, 1 minute. Okay, we can continue. So this is one conventional method of modeling the welding heat source. So we already succeeded in modeling this particular welding heat source, that is a macroscopic level modeling we already completed. These are some results showing the welding heat generator that we created using this heat source models. And we were able to compare these. Both results are from my own literature. These results are in the middle figure. We are comparing an actual weld pool created with a simulation. We were able to simulate the weld pool creation successfully. So this research is already over. This almost connected to TIC welding also, or welding heat source also. Standard data is available in literature. And the second part is melting process. This particular heat transfer analysis is valid, useful for the welding process. But coming to the CFD, coming to the VAM process, where the melting on metal formation and liquid metal formation and solidification process is having more importance. The second level of modeling is more important for VAM process. Now we just started with the CFD simulation of this VAM process, and this shows a domain that we just working with. It is a 2D system. It's showing a vertical nozzle. It's actually a vertical system only, with 1.1 mm diameter and 1 mm length only. It is nozzle is on the top portion, and the remaining rectangular portion is an air column. Using some techniques, we are modeling, and we were successful in creating the liquid droplet formation using this model. As you can see in this particular diagram, this you can visualize the droplet formation. The bottom portion, the top portion shows the torch, and the bottom liquid formation is there. Droplet formation is there, and the second figure shows the detached droplet. It is coming downward. So using ANSYS ANSYS software and using some additional parametric coding and all, we were able to generate this droplet formation. This is the fundamental thing of modeling of VAM process. And this is a video showing I hope this droplet formation is visible to you. Can anyone respond? Is that animation is visible to you?
Yes, sir.
Okay, thank you. Okay, so we were able to simulate this droplet formation. And one more advanced research required in this particular area is If you want to model additive manufacture or VAM process, if you want to model VAM process properly, you must consider the drop detachment and the flow of a particular liquid metal drop from the torch top to the bottom substrate. This is what is happening in the VAM process. There will be at the top, there will be a torch which will be providing an electric arc, and normally an filler wire or this particular electrode will act as a source of solid metal, and it will be melted, and that particular drop will come down and it will fall on the substrate on the bottom. By drop, this liquid metal will fall on the substrate, and in the building process will be taking place on the substrate. So in addition to modeling of droplet formation and its flow, we want to study more about the movement of this particular liquid droplet from the torch strip to the bottom substrate. For that, we have to do a proper heat transfer analysis. And for that, we conducted another study where, without considering the nozzle, just considered as a air column where droplet will be moving from the top to the bottom. This shows the computational boundary condition. And these are the methods used for solving this 2D problem. Here, the drop means it is a liquid metal which is flowing under gravity. Its temperature will be, if it is aluminum, it will be around 1000 degrees Celsius. If it is steel, then definitely it will be more than that. So it is a high temperature liquid metal drop falling from top of this column to the bottom wall. Here, the two sides represent pressure outlet. That means it is atmosphere. And at top portion, we are applying a velocity. By mistake, it is showing pressure outlet here. We are applying a velocity there. We studied the flow of that metal droplet. And this shows the conditions used for that particular analysis. These are the properties. We did it for aluminum material. And these are the governing equation and corresponding material properties. And we were successful in generating this droplet flow from top to bottom. And we got an interesting result of there is a 15-degree cooling when the droplet is traveling from top to bottom. The importance of this particular diagram is that if this cooling goes below its solidification temperature, definitely it will result in some sort of defects in the case of VAM. So this is an important result that we obtained using this particular analysis. As I already explained, the three levels of this particular diagram shows the three levels of VAM modeling. One is macroscopic level that I had already explained, and we are successful in modeling that. Currently, we were working on the middle one. But the research world outside India is, we are normally in case of research, we will be comparatively back. So they are progressing with molecular dynamic simulations. See, this is a paper published just in this year. It is based on the microstructure property correlation. So it is coming under the third category of modeling, that is molecular dynamics. They are simulating molecular dynamics. But if you want to go for molecular dynamic simulation, definitely you have to complete the liquid metal travel and all. Then only you will get the proper temperature variations and all associated data that must be utilized for doing molecular dynamic simulation. So the research outside the world is progressing. We are working on this particular area also. More number of papers will be published in coming years. And next, what I'm planning is advanced additive manufacturing methods. It includes printing of multi-materials, alloys, and composites. So this diagram shows some advanced method for optimizing mechanical properties in VAM. So while explaining this session, I already discussed these are the major defects that we are facing nowadays. Researchers are suggesting solutions for these particular defects, and this slide explains some solutions for overcoming those particular defects commonly observed in VAM products. We can explain it in coming slides. So here, one major method suggested for VAM is ultrasonic vibration. Here, during VAM process, that is during building process, the bed of that particular substrate will be vibrated using some ultrasonic vibration generator, or it can be a normal vibration or ultrasonic vibration. Both vibration have some sort of importance. These vibrations will reduce the residual stresses. That is one major advantage of this advanced VAM method. Actually, I think no industry is utilizing these sort of techniques now. All the things explained in this slide is only in research level, I think so. So the first methodology is for utilizing ultrasonic vibration during VAM process. Second methodology that can be utilized is magnetic field. One major issue with the welding arc welding is we are expecting a narrow bead, a narrow droplet. In case of VAM, it is a narrow droplet we are expecting. But due to limitations of this welding arc, normally a wide bead width will be there. By applying a suitable mechanism, by applying magnetic field, we can control the welding arc. By virtue of that, we can control the bead width. So the second advancement in this process is application of a magnetic field. Then comes the third one. It's a rolling. Immediately a rolling device will be there. A rolling ball or roller, it will be there. There will be, I hope the pointer is visible. There will be additive manufacturing or the VAM torch will be there. It will be depositing layer by layer. Immediately after deposition and solidification, that hot metal will be rolled using a roller. This is an additional process by which we can improve the quality of this VAM product. Okay. Another thing is peening. Peening is nothing but simple balls. It's like hammering. Simple rotating balls will be there. Just like vibration, ultrasonic vibration, this ball will be simply falling on that particular build area, it will give a small vibration and its stresses and properties will be rearranged. So this is another one advancement in case of WAM. And then comes laser arc additive manufacture or laser arc WAM. Here, in addition to the normal welding torch, an additional laser beam will be utilized. The welding torch have some limitations. The arc width is a limitation. Normally, we cannot control the width of the arc easily. Our control of arc is not easy in case of a thick welding torch. Here, that limitation can be adjusted utilizing an additional laser beam along with the welding arc. That is one advancement in WAM. Then, these are the proposed advancement in case of WAM that make utilize the WAM process for composite alloys and multi-material printing. See, this is a paper published in last year. Here, they are utilizing some method for material diversity. Material diversity means normally in WAM process, we'll be making use of a single feed wire. That feed wire will be a single material. So normally in WAM process, using the basic technique, we can build single material only. But here they are suggesting some methods for improving the capacity of WAM for printing multi-material. It's a paper published in last year. Here they are suggesting three methods, and they had did some experiments on these also. Some results are also available. It is shown. It is not shown there. If you are interested, you can take a screenshot of this slide. You can get this paper. Here, the first method that utilized is at the place of one wire, they used two solid wires. So two materials will be melted together, and that drop will be directly going to the substrate, and where that particular material will mix together. Here, even with a controlled wire feeding system, we cannot achieve a correct composition. We cannot achieve an expected composition on the bottom substrate because the welding arc is a highly unstable thing. So even if you are using two solid wires, definitely both will melt and it will go to the substrate. But may not be able to control the exact composition utilized by this method. So it is a basic thing. You can use one more additional wire for printing of multiple material that will enable this WAM process for printing alloys and composites. The second method they are suggesting is they are proposing a standard wire type filler material in which more than one type of material will be wounded as a wire. Different material, more than one, two, three, four, or depending upon the combination and depending upon the requirement, you can have a wire type filler material. Here, depending upon the size of each strand, almost we can control this particular composition of the substrate. And the next thing is they are suggesting use of a hollow type filler material, and in that in this middle portion, annular portion, they are filling some materials. It can be an additional alloying material. It can be a composite filler material. So they are suggesting a hollow tube type filler material for WAM process. So these three techniques were suggested in by these researchers in their paper published in last year. For that, this will make utilize VAM process for printing of alloys and multiple materials. And this is a paper published in this year itself, where they are suggesting an special type machine in which before the it is actually not particular with the VAM only, not with the VAM. It is for the another. Uh, it is applicable to the other type of additive manufacturing techniques also. Here, two jets will be there, or two knobs will be there. First knob will be placing a reinforcement fiber in the substrate, and that fiber will be fed from another feeder mechanism. You can see on this figure the filament, just it is showing manufacturing as a composite. First feeder is feeding a wire to the substrate, and above the wire or in and around the wire, the second nozzle will be doing injecting next matrix component of the composite. So this is another, this is the strategy suggested by these researchers. They were successful in creating that composite, this fiber reinforced composite. And this is also a paper published in 25 this year only, where a three nozzle system they are suggesting for uh, three nozzle system. In through one nozzle, short fibers will be injected. Through the other nozzles, matrix part will be injected. So they are suggesting a three nozzle system for printing of composites. So I am almost concluding with my presentation. So this particular slide shows the future of additive manufacturing, VAM or any other additive manufacturing, especially in case of composites and alloys. VAM is the most processing method. Here, multi-material, composites and alloys. These three things are the future promises of VAM: multi-material, composites and alloys. In case of alloys, as we explained in last slide, using special type of filler materials and using controlled melting we can achieve. And in case of composites, actually a digitally connected, more advanced equipments we need for printing composites. As we as already explained in this particular thing, this is a new machine with a head for feeding filler wire and another head for feeding the metric side. Just like in case of composites, we need more equipments, more advanced equipments for printing of composites. So connecting of this VAM machine with digital systems, we will be capable for, we will be generating more efficient systems in future. So I'm concluding my presentation with this particular slide. So utilizing this VAM technique, we will be able to generate composites. And just like in case of now, they are printing rocket engines using VAM technique, but it is not utilizing composites. Their metal VAM is utilized. In recent years, definitely there will be VAM machines for composites also. Using that, it will be commercialized. Now, in nowadays, it is only on the research stage. It will be commercialized shortly. So it is a future research area. So we can expect more wonders in this area short. So now the forum is open for discussions. If you have any queries, you can ask now.
Okay,
Am I
thank you, sir. Informative session. Dear participants, now it's your turn to raise your questions or queries related to this topic. And you can also unmute your mic and ask your questions, or you can use chat box for posting the questions. So we have a question in the chat box. What key advantages does material extrusion additive manufacturing offer when using recycled discontinuous carbon fiber reinforced thermoplastic composites?
Can you repeat that? I am not able to see the chat now.
What key advantages does material extrusion additive manufacturing offer when using recycled discontinuous carbon fiber reinforced thermoplastic composites?
Yes, this recycling of recycled material, use of recycled materials is another area. Met, I seen so many purpose on that area. It is another area. Normally, this recycling is possible in case of composite materials. It is another area. So many research is going on that. N number of advantages is there because nowadays this recycling of plastic is a social issue. Many researchers are trying for finding out its solutions. Definitely, it will add advantage to the uh, additive manufacturing system.
Yes, sir. Participants, do you have any other questions?
Okay, if you don't, am I audible?
Yes, sir.
Okay. So I'm representing College of Engineering Trivandrum, and we have a lab there. Then we have utilizing the ANSYS research license available there for doing this sort of research. And we have short-term course on 3D printing, and we have a product development center at College of Engineering Trivandrum. We are offering internships and short-term courses on 3D printing. If you have any related requirements, you can get my number and you can contact me. Anyway, thank you. Thank you for your patient listening. Ma'am, over to you.
Thank you, sir. On behalf of the organizing committee and all the participants of FDP, I extend my sincere gratitude to our distinguished resource person, Dr. Joy Varghese, sir. Your talk has enriched our understanding about this session. And also, I'm welcoming Ms. Anju ES for giving the thank you.
We sincerely thank you for delivering an insightful and highly informative session on additive manufacturing of an advanced composite materials. Your detailed explanation, real-world examples, and expert insights provided our participants with a deeper understanding of the latest advancements in this field. Your session has undoubtedly enriched the knowledge of everyone present and inspirational for the learning and exploration. We are truly grateful for your valuable time, efforts, and willingness to share your expertise with us. Thank you once again for an excellent, impactful talk. Thank you very much, sir.
Thank you.
Okay, dear participant, feedback for this session is posted on the chat box. Kindly fill it. Once again, thank you, sir. Now it's time to start our next session, session 8. For this session, I'm delighted to welcome our resource person, Dr. Anju Chandran. It is my privilege to introduce Dr. Anju Chandran, an accomplished researcher and scientist whose work spans some of the most dynamic and evolving areas of materials, engineering, and device innovation. Dr. Anju Chandran earned his PhD in engineering from the Academy of Scientific and Innovative Research at the CSIR National Physical Laboratory in New Delhi, where his doctoral research focused on the dynamics of liquid crystals at interfaces with the invisible structures for advanced device applications. Professionally, Dr. Achu Chandran serves as a scientist at CSRI NIST Thiruvananthapuram, a role he has held since 2019. Prior to this, he worked as a scientific scientist at CSIR, CEERI, Pilani, and as a quick hire scientist at CSIR NPL. New Delhi, reflecting a strong and steady trajectory of excellence within India's premier scientific research institutions. Dr. Achyuchandran has also been widely recognized for his achievements. He is a recipient of the Early Career Research Award from DST SERV in 2019, the Young Scientist Award in 2017, the prestigious DAP Fellowship and CSIR Senior Research Fellowship. With his rich academic background, impactful research, and commitment to scientific innovation, he has he has vast experience and insights make him an inspiring figure in the engineering and material science community. Please join me in giving a powerful virtual welcome to Dr. Achu Chandran, Principal Scientist, CSIR NIST Trivandrum. We are eagerly look forward to his session. Once again, welcome, sir.
Dear participants, kindly note our second session resource person is getting some more time to join with us. Kindly cooperate with us. He will join on 7:45. Let's take a short break now. Kindly cooperate with us. We will restart our session on 7:45. Our resource person will join on that time. Now we will have a short break.
Dear participants, if you wish, be on the line. Else, you can rejoin at 7:40. We will start the session at 7:40.
Hello. Am I audible? Hello.
Yes, sir.
Yeah.
Okay, sir.
Shall we
Can we
start?
start the session?
Yeah, I'm ready. So if everyone is here, then we can start.
Okay, sir.
Hello.
Sir. Sir, please wait 2 minutes. The participants are joining now. Dear participants, welcome back. Now it's time to start our session 8. For this session, I am delighted to welcome our resource person, Dr. Akshay Chandran, an accomplished researcher, scientist, whose work spans some of the most dynamic and evolving areas of materials engineering and device innovation. Dr. Achyut Chandran earned his PhD in engineering from the Academy of Scientific and Innovative Research at the CSIR National Physical Laboratory in New Delhi, where his doctoral research focused on the dynamics of liquid crystals at the interfaces with the immiscible structures for advanced device applications. Professionally, Dr. Achyut Chandran serves scientist at CSIR NIST, Thiruvananthapuram, a role he has held since 2019. Prior to this, he worked as a scientist at CSIR, CEARI, Pilani, and as a quick hire scientist at CSIR NPL, New Delhi, reflecting a strong and steady trajectory of excellence within India's premier scientific research institution. Dr. Hutchison has also been widely recognized for his achievements. He is a recipient of the AV Career Research Award from DST SERV in 2019, the Young Scientist Award in 2017, the prestigious DAT Fellowship, and the CSIR Senior Research Fellowship. With his rich academic background, impactful research, and commitment to scientific innovation, through his vast experience and insight, makes him an inspiring figure in the engineering and material science community. Please join me in giving a powerful virtual welcome to Dr. Achyut Chandran, Principal Scientist, CSIR NIST, Trivandrum. We eagerly look forward to his session. Once again, welcome, sir. Welcome to the session.
Yeah, thank you. Thank you for the nice words of introduction. So today, shall we start? Hello.
Yes, sir. Yes, sir. We can start the session.
Yeah. So before going into the session, I would like to place on record my sincere thanks to the organizers of this particular event, especially Dr. Praveen and his co-workers for giving me a chance to showcase our activities in this particular area. Hello.
Sir, it's
Hello.
audible. Sir?
Yeah. Yeah. Okay. So I'm sharing my slides. So is my screen visible?
Yes, sir.
Okay.
Yes.
Yeah, now it is in full screen, I guess.
Yes.
Okay. Yeah. So in today's faculty development program, we will be seeing the future-ready flexible devices for energy, wellness, and environment. So I'll be keeping the session in like 40-45 minutes. Next, we will be discussing about basically next generation devices. So myself, Dr. Chuchandran, I'm working as a principal scientist in Material Science and Technology Division of CSIR and IST Trivandrum. So we are basically into flexible and printed electronics. So before going into the session, let's see the status and scope of printed electronics in India. So why indigenization of printed electronics is important? As we know, there is an increased demand of advanced printing technologies, high quality conductive inks, energy efficient electronics and compact devices in our country. and 90% of electronic components are being imported in our country. For a country to be self-reliant in their strategic electronics and societal structures, we need to indigenize their electronic technologies. And if you see the global market of flexible and printed electronics, it is coming around 37.1 billion US dollars, including displays, logic devices, batteries, organic photovoltaics, electronic textiles, conductive inks, sensors, and OLEDs. And in this particular segment, printed electronics alone is having a market of around 20.7 billion US dollars. And that is, as of today, it is going with a annual growth rate of around 21.5%. So in summary, in India, the demand of affordable and printed electronic components are very high, but there are no market-ready technologies available. So our activities are in line with Make in India, Atmanirbhar Bharat, and Vikasit Bharat Abhiyan programs of Government of India. So against this background, I have joined CSIR NIST Trivandrum, National Institute for Interdisciplinary Science and Technology, Trivandrum, in the area of electronic materials and devices. So basically, we are into customized substrate development, functional ink development, and printed devices out of that. Printed devices such as wearable fabric heaters, triboelectric nanogenerators, lead-free piezoelectric sensors, and electronic skin are the areas of our interest. Some of the devices what we have fabricated in our lab is being showcased here. So in between, like if you are getting any disruption in connection, or if you have any queries, you can stop me and you can ask. Okay, since it is an online session, I don't know whether you will be well connected, or you may have any queries in between. That's why that feedback is important. Hello, I think till now everything is clear. Hello.
Very clear, sir.
Yeah, okay. So you can see our facilities, especially in the area of printed and flexible electronics at NIST, that include facilities for material processing, then optical characterization facilities, photolithography, then thermal characterization facility, electronic, then ferroelectric and ferromagnetic kind of testing facilities, including PPMS. PPMS is like physical property measurement system. That is one of the unique facilities available only in 2-3 places. So one among is CSR NIST. We also into like energy harvesting kind of applications. So the facilities which is required for energy harvesting applications, especially mechanical energy harvesting application and EMI shielding applications are available with us. So in material processing, we have tape casting facilities, isostatic lamination, inkjet printers, semi-automatic screen printers, and electrospinning. So we also have thermal evaporators for electroding and other purpose. So all kind of like photo, then electrical, electronics, thermal, and optical characterizations are available with us. So one of the key activities in this particular area is the development of materials for printed electronics. So it is one of the important strategic substitution electronic activity, because most of the electronic components what we are using as of now is being imported in our country. As I mentioned in the introduction, 90% of components are being imported. So this activity has its own importance, especially in strategic electronic sectors, as we develop various kind of customized substrate, printed ink, including conductive inks, dielectric and piezoelectric inks. And in customized substrate, we are basically into LTCC and HTCC substrate. So what is LTCC? LTCC is nothing but low temperature co-fired ceramic technology. So you might have seen the MEMS technology. So some of you might be familiar with the word MEMS, micro electromechanical systems. So whatever devices you are making on silicon substrate. Okay, so that kind of technology, especially in micro scale and meso scale, is called as MEMS, with the mechanical and electronic parts and actuation and all those things. So those kind of MEMS based devices need precision packaging. So that packaging is being provided by LTCC technology. Okay, and LTCC itself is a technology where you can print various devices on different layers and stack them together, and after firing, that will become a single unit. So that is very important for the system development, that too reliable systems. So the firing is happening at around 850 degrees Celsius. The system is very much reliable. And in green stage, the LTCC tapes are flexible. So these are machinable kind of ceramic tapes. So you can drill holes, you can like make cuts, wires, and different kind of structures over that. And the stacking of these things will give a complete module. So different functionalities can be incorporated into different layers, and subsequently the complete system will address for a particular application. So some of the customized LTCC tapes developed at NIST is shown in the figure, and LTCC tape along with the conductive inks like gold and silver ink, which is being printed on the tape which we have developed, is being shown in the bottom slide. Okay. So some of the functional inks what we have developed is like conductive and dielectric, and also the piezoelectric kind of thing is being showcased in this slide. So you can see the silver ink, multi-wall carbon nanotube ink, and sodium potassium niobate. That is basically a piezoelectric, lead-free piezoelectric. So these activities is being supported by various funding agencies, including BHEL, ISRO, DRDO, and DST, like that. And some of the companies like Karnataka Hybrid Micro Devices, Aron, Taclox, Celes, and Ceramics are on board with us. And one of the key area, like we are collaborating with ISRO SAC Ahmedabad, is the development of space qualified LTCC tape and compactable gold paste. Currently, the LTCC tape and gold paste being used for space qualified applications are being imported in our country from Physics or DuPont. So ISRO want to indigenize this technology. They came to us and we together developed this LTCC tape and compactable gold paste for hybrid micro designs, especially for the communication application. So very recently, we have received a Solar Grand Challenge Award from DST. So it's costing around 4 lakh US dollars. So that is approximately 350 lakhs. And in this particular project, we are partnering with BHEL for development of commercial grade low temperature curing silver paste. You might have seen for solar cells, there are finger-like patterns. Silver conductive tracks are being printed on solar cell for collecting effective like charge carriers. So the current the paste, whatever being used by the Indian solar industry, is being imported from DuPont, Harris, and Dicotech. So Harris is one of the key player where BHEL is currently importing. So if you see the NIST developed solar paste, especially the silver paste, some of the parameters like viscosity, sheet resistance, drying conditions, and solid loading, this is par with the international standard. So in this particular activity, we are partnering with some of our collaborators like Dr. K.P. Surendran, and from BHL side, there are some collaborators for the ink testing and all. So you can see the schematic of conductive solar paste development, starting from various precursors like silver nanowires, silver nanoflakes, and silver powders, which is being added into solvent and dispersant systematically and homogenizing, then adding different kind of binders, plasticizers, humectant, and thixotropic agent. We are forming the ink. Then deformers and different process like roll milling kind of things are being adopted for the ink formulation. And finally, by using screen printing technology, you can print or transfer these patterns to HDT solar cell. So the very first device what we have developed on this particular technology is a room temperature curable carbon nanotube ink for the very first time. So normally in printed electronics, after printing your conductive tracks or the functional ink, you need to treat it either with the temperature or with the photonics. So if it is with the photon, it is called photonic sintering. If it is with the thermal curing, it's a temperature curing kind of setup is required. So here the ink what we have developed is a room temperature curable one. That means you can print it and forget it. No need of any post processing. So that is very energy efficient kind of technology. So on a plastic substrate, which is called a mylar substrate, we have printed a room temperature curable carbon nanotube ink, which is formulated by well mixing of multi-wall carbon nanotube along with the P.PSS, which gives binding, surfaction, and conductivity. And this particular ink, if you are applying a bias voltage of like 7.5 volt, the printed pattern were able to generate a temperature of around 125 degrees Celsius, that too uniformly on the whole surface that you can see here. Yeah. So you can see here the uniform temperature distribution. And if you look into the electrothermal characteristics of this particular ink, for reaching a temperature of around 136 degrees Celsius, it is merely consuming almost 137 milliwatt per meter square. So that much low power consuming it is. And if you see the on-off characteristics of this particular heaters, within 10 seconds of time, it is getting to the maximum temperature of 120 degrees Celsius. And again, if you switch it off, it will come back to the room temperature within again another 10 seconds. So these results a couple of years back, we have published in Applied Materials Today. Then at the time of COVID-19, utilizing our knowledge of developing various kind of flexible and printed heaters, we have developed a self-sterilizing fabric heater. So that is basically for PPE applications. So in personal protective equipments, the motivation behind this particular study was there appeared a report in WHO, World Health Organization's website, stating that heat at 56 degree can kill SARS coronavirus with a rate of around 10,000 units per 15 minutes. And almost at the same time, an article appeared in Lancet Microbe in 2020 stating that the time of SARS-CoV virus inactivation can be reduced to 5 minutes if you elevate the temperature from 56 to 70 degrees Celsius. So at the same time, a group of researchers from Israel has come up with a face mask technology where they were using carbon fibers for heating the face mask. And these carbon fibers were able to give a temperature of around 70 degrees Celsius, that too within 30 minutes of time. That means if you are applying 5-volt bias in 30 minutes, if you are continuously supplying 5-volt bias, the surface of these carbon fibers will reach a temperature of 70 degrees Celsius. So the ink, almost at the same time, the ink and the heater technology, what we have developed is basically a fractal pattern based one that is being shown here. So we have printed our silver ink on polyester by using Hilbert pattern, which give a temperature stability of around 125 degrees Celsius over the complete area. And we have developed a 4x4, 4.5 to 4.5 centimeters square active area heater, which were able to get a temperature of around 120 degrees Celsius, that to application of 5-volt. And the power consumption of these particular heaters are 240 milliwatt per centimeter square. You can see that within 30 seconds of time, we could able to reach 120 degrees Celsius. Why 120 degrees Celsius? 120 degrees Celsius is the standard sterilization temperature above which any kind of microorganisms cannot withstand. So apart from SARS coronavirus, any kind of microorganisms cannot withstand on this particular temperature. And that too within 30 seconds of time, we could able to achieve a temperature of 120 degrees Celsius. So that is like significant. So various design and simulation studies has accompanied with this particular study, and that has led to this particular development of self-sterilizing fabric heaters. Then we have integrated this self-sterilizing fabric heaters into a stopgap kind of face mask and successfully tested it against gram-positive and gram-negative bacteria. So you can see the various layers of these heaters, which is being developed by using 3D printing. So this is called a stopgap face mask. This is a patented technology, wearable fabric heaters integrated face mask. And for this particular invention, our group has been recognized by various awards, including CSIR Young Scientist Award from CSIR India, which has been highlighted in Hindu a couple of years back. The same technology which we have developed for this self-sterilizing fabric technology, we have extended it for thermotherapy kind of applications. So we incorporated our fabric heaters into a smart band, basically the pressure bandage. So then we demonstrate the same technology for musculoskeletal treatment kind of applications. So you can see that the design, simulation, and various kind of testing what we have done on this particular smart band is being showcased here. So flexibility and reliability study has been accompanied by this one. So without you can continuously do any flex or any kind of multiple cyclings. So it won't alter the temperature distribution on this particular area. And along with the heater, we have developed a printed temperature sensor and a custom-made circuit for a feedback kind of mechanism. That means you can set a particular temperature. Suppose if I need 35 degrees Celsius for my health musculoskeletal kind of treatment, then I can set a temperature of 35, and after attaining the temperature, it will automatically cut off. So that is the importance. Okay. So fabric heater integrated thermotherapy device is being showcased here, and this can also be extended for various kind of sports medicine kind of applications, and it can replace like hot water bags. So in traveling and all, this is very convenient, like battery operated kind of mechanism. And again, you have a controller. So user defined temperatures can be set on that. So we have extended this particular technology for cold deserts, especially self-regulating wearables for cold deserts. It's an important technology for DRDO and Indian Army. So the power consumption of smart gloves, warm insole, and the warm jacket, what we have developed are like 2 watts, 5 watts, and 12 watt respectively. And the temperature range and operation voltage range and all those things are being showcased here. You can see the corresponding video also. So currently we are in discussion with the DRDO CVRD Avadi, who is interested in this particular technology. One another important area where we are into is like nano generators. So what are nano generators? So basically nano generators converts mechanical energy into electricity. So those are called like triboelectric nanogenerators or piezoelectric nanogenerators. Piezoelectric nanogenerators are like conventional technology where dislocation of dipoles are basically used for harvesting mechanical energy. So in triboelectric nanogenerators, contact electrification along with electrostatic induction is being utilized for energy harvesting kind of applications. So working of piezoelectric nanogenerator is being showcased here. So for the very first time, piezoelectric nanogenerator has been developed by Professor Isidel Wang of Georgia Tech in 2006. That is on zinc oxide nano ribbons. Later from the same group in 2012, a new technology called triboelectric nanogenerators has been evolved. So basically, as I mentioned, it is based on contact electrification and electrostatic induction. You can see that when two material which are dissimilar in their electrostatic series are coming in contact, at the contact, like different charges, like positive and negative charges are getting formed because of this particular friction. And once they are separated apart, in order to compensate the charge, electrostatic induction is happening on the backside of electrodes. So once you connect these electrodes to an external circuit, current can like flow in a particular direction. So this particular technology find applications in powering electronic gadgets and personal gadgets, including microwatt and milliwatt power consumption range. So those include IoT-enabled devices, cardiac pacemakers, Bluetooth devices, micro heaters, and MEMS sensors. So coming to the nano generator devices, the very first device what we have developed is a spring-assisted kind of nano generator, basically by using like PVDF and PMMA kind of films which are spin coated on copper. So the power density what we have got is around 2 milliwatt per meter square. So you can see that on finger tapping you are getting almost like 100 volts, and if you are doing palm tapping again, the force is increasing and proportionally the output voltage is also increasing, and if you are doing like toe tapping again the output is increasing. And this we have demonstrated for powering various kind of electronic gadgets, including calculators, then thermometers, LEDs, and all. Further, we found that if you incorporate certain kind of two-dimensional materials like hexagonal boron nitride is called white graphene. Okay, if you incorporate these kind of like 2D materials to one of the contact layers of a triboelectric nanogenerator, the effective area will increase. And substantially, you can increase the power output almost like 20 times. So in this particular case, when we have developed a boron nitride nanosheet BOPT assembly against a paper, we were able to get a power output of around 0.14 watt per meter square, which we have published in a flagship journal in the area of energy, that is nano energy. Again, we found that if you do micro patterning on both the contact surfaces, like micro patterning on the PDMS side and on electrospinning on the cellulose side, and the coupled device will enhance the power output almost 180 times. Okay, so the voltage is increased to almost like 400 volt, current to like 3 milliampere per meter square, and power density to almost 0.9 watt per meter square. And this has been tested for the almost 10,000 cycles and all. And this particular invention or the particular finding we have published in Nano Energy in 2022. So apart from these materials, we also developed various kind of nano generators, triboelectric nano generators from waste materials such as polypropylene, which is derived from used surgical mask, has been used as one of the contact layer. And the mylar material, which is basically used for the packaging application, has been taken as the other contact layer. And the system, the complete system has developed, and the power output what we have got out of this particular combination is almost like 11 milliwatt per meter square. So this we have published in ACS Applied Materials and Interface. So again, by using this particular combination, we powered various kind of electronic gadgets. And almost at the same time, like our industry is into like lead-free kind of piezoelectric nanogenerators also. So we developed various kind of lead-free piezoelectric nanogenerators, printable piezoelectric nanogenerators based on sodium potassium niobate ink. Okay. So you can see that a 4x4 array of sensors what we have printed on a flexible substrate is being shown here. By using an interface circuit, we could able to get crosstalk free kind of signals from all the 16 channels at a time. So that means if you are touching one particular pixel, the other pixels are not disturbing the signal output. So independently, you can take signals out by using this interesting interface circuit. So this has been done in collaboration with the National University of Singapore a couple of years back with the Professor Cheng Hu Yi. Yeah. So this year's earmark the Nobel Prize in the area of actually the chemistry Nobel Prize for this year has been in the area of metal organic frameworks. So these are the like inventors of metal organic frameworks for the co-development of metal organic framework. Zuzumo Tagawa, Richard Robson, and Omar Yagi. So these people have received the coveted Nobel Prize. So we also work in this particular area of MOF. For the very first time, we found that the triboelectric nature of a particular polymer, like polyacrylonitrile, can be tuned either to the negative side or to the positive side by wisely choosing the MOF material. So if you are taking 1100 and HQST as a dopant to PAN, you can increase the tribopositivity. And if you are taking CIF65 and CIF8 as the dopant, you can increase the tribonegativity. So the electron donating and electron accepting nature of a particular like polymer can be tailored by using various kind of MOF materials. So this is the very first finding in this particular direction. And we also developed a various kind of self-powered humidity sensors and tactile sensors on this particular technology. And this has been published in the flagship journal Advanced Functional Materials early this year. We also hold a patent on triboelectric nanogenerators for harvesting kinetic energy from food stamp. So by wisely choosing the materials, by dielectric tuning, multi-layer integration, and high output kind of device has been formulated, which are durable and stable. Then this particular device, what we have developed on a spring-assisted structure, has been integrated into a shoe. So that resulted in almost 4.3 kilowatt peak-to-peak electrical output, 45 microampere current, and 20.25 watt per meter square, which is a record power density. And this has been utilized for powering various kind of electronic gadgets and direct powering of like LEDs. So that in this video you can see. So we entered into hybridization of nanogenerators. So we coupled like triboelectric nanogenerators along with electromagnetic generators for maximizing the energy output. You can see that we have developed a machine called Vidyut Swasthya, which can burn your calories and power the world. So basically, it's a human-powered charging system, generate energy from simple pedaling. And we are getting a regulated power output like 230 volt, 50 hertz, and 2 amps. This is basically an engaging and interactive kind of device with the modular design. So you can do exercise and charge your mobile phone. You can burn the calories, and in real time you can see the status. So that is basically CSR NIST's hybrid generator technology. So in this video, what you are seeing is the hybrid generator developed by our team, which is being demonstrated to the Honorable Minister of Science and Technology, Dr. Jitendra Singh. So our nanogenerator technology is going into the industry level. So it will very soon will be coming into market. So we are tying up with India's #1 tire company MRF Limited for development of smart tires. So we are integrating nano generators into the conventional tire and developing an energy harvesting system along with energy storage and device powering kind of mechanisms. A smart monitoring and warning system will be developed with the help of with the funding support of MRF. So some of the prototype device, like the tire rotation device, has been shown here. NIST smart tire prototypes are being shown here. So which is being integrated with various kind of arrays of nano generators. So on tire rolling, you can convert those pressure which is being imparted on the tire into electricity. So that can be used for powering various kind of gadgets. So we never stopped there. Basically, our triboelectric nanogenerator technology is going to Mars as well, like to space as well. So we handholded with ISRO for development of energy harvesting from Martian environment technology by using triboelectric effect for powering smart sensors. So this will be part of ISRO's Mars lander mission in 2028. So we have developed a wind energy harvesting system. So the problem with the Mars is like almost 40% of sunlight is reduced. Means almost 40% of sunlight is less in Mars. So in order to compensate in solar missions, in order to compensate in the space missions, you need a secondary power source. And the advantage with Mars is abundant with triboelectrically charged particles. So why can't we convert these triboelectrically charged particles for harvesting the wind energy from Mars, and that can be utilized for powering various kind of sensor node deployed as part of the mission. So that thought has arrived at this particular collaboration with ISRO. So we will be powering various kind of sensor node developed by ISRO by using our own nano generator system by using a power management circuit. So we also develop various kind of vibrational sensors, especially piezoelectric nanogenerator based vibrational sensors. So a self-powered vibrational sensors based on electrospun PVDF barium titanate nanocomposite nanofibers is being shown here. You can see that this sensor, when it is being attached to a CPU fan, and the fan is rotating with the normal vibrations without any fault. So you are getting a particular profile. Whenever you are employing some sort of additional weight to one of its pins, additional vibrations are getting generated. And real time, you can map those vibrations. Likewise, you can predict the fault which is being occurred in a machine. So if you take the frequency domain analysis, like FFT of this particular signal in normal operation and under fault condition, you can differentiate the frequency signatures. So that we have published in AC supplied materials and interfaces. And currently, this lead-free piezoelectric vibrational sensors we are deploying for structural health monitoring applications. So we have formulated a project consortium with SCRC Chennai, Structural Engineering Research Lab of CSIR, and a couple of Indian industries, including L&T. L&T Construction is interested in this particular technology. The current technology used for structural health monitoring applications are lead-based systems, which are not environmental friendly. So mainly PZT kind of material, like sodium. PZT is like lead zirconate, titanate kind of materials are being used. So as an alternate, we are developing like potassium sodium niobate kind of materials and barium titanate kind of materials, which are lead free. And the other kind of structural health monitoring like sensors are battery operated, like accelerometers and all. So as an alternative to this particular technology, indigenous self-powered lead-free piezoelectric vibration sensors we are developing for energy harvesting as well as structural health monitoring application. So some of the piezoelectric ink developed in our lab is being shown here, and the piezo fiber mat is also shown here. So we have signed an MOU with these particular companies in this direction. So finally, we will be having a vibrational sensor, then data acquisition system, wireless data transfer, and real-time monitoring. So the technology readiness will be enhanced to like TRL6 and all at the end of this particular project. So our interest expand to electronic skin as well, especially for tactile sensing kind of applications. So mimicking human skin is very difficult. So that is a technology gap. Like we have multitude of sensors. So basically, our interest is like to develop like tandem architectures. Okay, so development of wearable electronic skin patch for real-time monitoring of human health parameters and tactile sensing, which is being funded by DST. So this particular project, we have developed various kind of capacitive tactile sensors for wearable pulse monitoring kind of application. And we also developed the tandem architecture of piezoelectric and the piezocapacitive sensors for real-time monitoring of pressures, especially static and dynamic, up to a range of 50 kilopascal. So that in this video it is getting demonstrated. So the pixel, whatever you are touching, is getting identified. If you vary the pressure in a particular pixel, so that variation is also being shown in numbers. So we also developed electronics kit for robotic kind of application and healthcare kind of applications. So that is being showcased here, especially for pulse monitoring applications, robotic arm, breath sensors, temperature sensors, and all. So in another 5 years, we are looking for like next generation transparent and stretchable electronic devices, multifunctional and wearable energy harvesting sensors, pilot scale demonstration of and technology transfer of printed materials and devices. So during that time, we will be developing major facilities like roll-to-roll inkjet printers and next generation electronics. So these are the international collaborations, including collaboration from Russia, France, Australia, Germany, Poland, Singapore, and United States of America. So various groups are collaborating with us. So these are research credentials. As a scientist in CSIR, I have published more than 60 papers with an average back factor of more than 7. Then 2 patents, 1 technology licensed, 4 chapters, and the conference proceedings around 30 plus. Awards include various BRICS Young Scientist Award, then International Academy of Engineers INE Young Engineer Award, Kerala State Young Scientist Award, CSR Young Scientist Award, and so on. Some of the publications from our group is being showcased here. So about the total projects I was involved in. So total projects is around like 24 projects with a cost of around 14.35 crores. Out of that, 8.8 crores are externally funded projects, including funds from MR of L&D Constructions, ANR of DRDO, ISRO, and so on. Acknowledgement. The organizers of FDP is again being acknowledged here for getting a chance to showcase our particular activities in this particular direction. Director NAST is being acknowledged, collaborators, colleagues, and PhD and project students, funding agency, and industry partners. So there is a short video of just 3 minutes, which will be showcasing our capabilities in this particular area. You can just have a look.
The future is flexible and foldable. The global electronics sector is in a paradigm shift towards flexible and wearable technologies since last decade. In order to address the reliability issues of conventional wired electronics, printed electronics technology is widely adopted in consumer and strategic electronic systems, where a variety of devices can be printed directly onto rigid or flexible substrates. In addition, the integration of various electronic components became easy, owing to the innovations in materials design and printing technology. More importantly, printing is faster than clean room technologies and ensures huge reduction in form factor of electronic systems. Against this background, CSIR, NIST Trivandrum, is in the process of developing electronic-grade materials for printed electronics, especially customized substrates, functional inks or paste, and devices out of these for strategic and societal applications. A smart mask for pulmonary health monitoring is developed with a printed piezoresistive strain sensor using silver-decorated CNT ink. The same ink is also used to develop a printed piezoresistive strain sensor, which transduces the hand gestures to a robotic arm. We have also developed a printed silver and carbon ink-based resistive heaters by replacing conventional coil heaters for various flexible and intelligent applications, such as smart band, warm insoles, warm jackets, and warm gloves. These products provide flexibility, lightweight, and a controlled temperature system to ensure the optimal condition for human comfort. Highly conductive silver nanoeye ink is used for fabricating flexible and wearable printed radio frequency identification tags. Recently, we have developed all printed electrochemical glucose sensors for sensing of free glucose in a serum. Apart from the printed electronics, CSIR NIST have its own signature in energy harvesting devices, especially piezoelectric and triboelectric nanogenerators that can tap into the low frequency and high entropic ambient energies, we have developed various piezo and tribo devices having rigid, flexible, and bio-based form factors. These devices can be used to power different electronic gadgets, even from biomechanical energies. In addition to that, self-powered pressure, vibration, tactile, and navigation fabricating flexible PSI are nearest, especially piezoelectric and triboelectric nanogenerators that can tap into the low frequency and high entropic ambient energies. We have developed various piezo and tribo devices having rigid, flexible, and bio-based form factors. These devices can be used to power different electronic gadgets, even from biomechanical energies. In addition to that, self-powered pressure, vibration, tactile, and navigation sensors are all being developed at NIST with excellent sensitivity and transparency. We are looking for research collaboration in conductive inks, printable and wearable sensors, triboelectric, as well as piezoelectric energy harvesting systems.
Yeah, thank you. So if you have any queries, we can have a discussion over here.
Thank you, sir. Thank you for your informative session. Dear participants, it's your time to ask questions related to the session, or you can unmute your mic and ask questions, and may you post the questions on the chat box. And also kindly that feedback from the session 8 is sharing the chat box. So we have some questions in the chat box.
Yeah, so yeah, and Shubinu is asking, how does the thickness of CND layer affect the heating performance of flexible heaters? Yeah, definitely. The thickness will affect, because once you vary the thickness, proportionally the resistance will vary. The sheet resistance, you know that the resistance of a conductor, that is rho L by A. So the layer thickness and the area. So those two things are important parameters. Once you increase thickness to a particular level, then the resistance will increase, and proportionally the current will decrease. So in that way, the heating, the parameters need to be tuned with an optimum range of layer thickness. And what are the typical firing temperatures? So basically for LTCC, the typical firing temperature is 850 degrees Celsius. So that is having a profile. And if it is HTCC, like high temperature coated ceramic, firing happens at around like 1500 to 1600 degrees Celsius. So the device is very stable up to that particular temperature. Then how to control the firing temperature? So it's being happening in a furnace, like it's HTCC, like LTCC box furnace is available with various profiles. Otherwise, like Nebertherm kind of furnaces can also be used for that applications. Okay, thank you. So if any other questions are there, you can just put it in chat box, or you can unmute and ask.
Once again, thank you, sir. On behalf of the organizing committee and all the participants of the FDP, I extend my sincere gratitude to our distinguished resource person, Dr. Achu Chandran. Your talk has enriched our understanding about this session. And now I am welcoming Achu Anju for giving the thank you note.
Sir, we extend our sincere gratitude to you for delivering an enlightening and informative session on advanced materials for printed electronics devices. Your expert insight, clear explanation, and in-depth knowledge provided our participants with a comprehensive understanding of emerging materials and their application in modern printed electronics. Your session has greatly enriched the learning experience and sparked keen interest among the attendees. We are truly grateful for the time and effort you dedicated to sharing your expertise with us. Thank you once again for your valuable contribution and excellent job. Thank you very much, sir.
Thank you, madam. And thank you all, especially the participants and the organizers. Shall we wind up here?
Yes, sir.
Yes, sir.
Thank you.
Thank you all once again for your time, attention, and contribution. Let's meet tomorrow for the next session with the same energy and curiosity. Thank you.